Now let's discuss about different rotations performed in an AVL tree. So first I will say about why rotations are required in an AVL tree. First of all, suppose that I need to insert the numbers 1, 2, 3 and 4 into a binary search tree. The normal insertion procedure will be 0, that is this will be 1, this is 2, this is 3 and 4. Okay. Now if you calculate the balance factors of each node, so first of all we need to calculate the heights. So this is height 0, this is height 1, this is height 2, this is height 3. Now one thing we need to notice is, suppose that if you are finding the balance factor of a tree, and suppose that there are some nodes which has only one child, then we need to take the height of the other child equal to -1. That is, for example, in this case, if you consider the node 3, the node 3 has only one child, that is node 4, and node 2 has only one child, that is node 3, and node 3 has only one child, that is node 2. In these cases we have to take the height of the left subtree of that nodes equal to -1. This is a special case that you need to understand. Now we are finding the balance factors of each nodes. So for node 0 we have right and left subtree same height, so this is 0. Now for node 3 we have the left subtree height equal to -1, right subtree height equal to 1, so the height here is, the balance factor here is -1. Now for node 2 we have the left subtree height -1, right subtree height 1, so we have -1 -1, that is -2. And for node 1 we have the left subtree height -1, right subtree height 2, so the balance factor here will be -3. Now I will just take only the balance factors here. So balance factor of each nodes are given here, so this has a balance factor 0. So if you look at this tree is not a AVL tree, not an AVL tree. Now we are trying to make this tree as an AVL tree. So what we have to do is we will have to perform certain rotations, so that after every insertion we will make sure that this tree is growing as an AVL tree. So this is not an AVL tree because we have balance factors -2, -3, etc., which are not allowed in an AVL tree. And you can see that all these balance factors are negative, which means that it is heavy to the right side rather than the left side. Yeah, so here we don't have anything on the left side, so it is weighing more on the right side by 3 nodes. Okay, now let's see what are different rotations performed in an AVL tree. Suppose that we have a case wherein we have nodes, like we have a node y, on the left side we have a node x, on the left side of x we have some subtrees, let's say t1, on the right side I have another subtree t2, on the right side of y I have another subtree t3. This is the structure of my tree, and this is the connection that is coming from the previous node or root. Now we want to perform a right rotation. So there are basically 2 rotations in AVL tree. The first one is right rotation, the second one is left rotation. Now first we will look at what is right rotation. Okay. So So we will see what is right rotation. So we are rotating y with respect to x. We are rotating y with respect to x. So we will fix the value of x there, then we will rotate whatever is on the right side of x. So one fundamental thing that you need to understand is whatever links comes to y should be connected to x after the rotation. So we will have the value of x on top, and whatever it is rotated to the right side of x will be on the right side. So on the right side I have y, to the right of y I have the subtree t3 sorry. Now on the right side of x I have t2, on the left side of x I have t1. So this is not a binary tree because this x is connected to more than two subtrees. So one thing we need to take care of is, if you find the in-order traversal of this tree, then first you will have t1, then you will have x, then you will have t2, then you will have y, then you will have t3. So this in-order traversal should be maintained after the rotation, otherwise the tree will not be a binary search tree. Or in other words, you have the value of t2 greater than x and you have the value of t2 less than y. So this condition should be met after the rotations also. So I'm taking these conditions here, and this has to be met after the rotation. So one thing you can do is, you have to make sure that t2 is greater than x. So t2 should come on the right side of x and t2 should be less than y, so t2 should be on the left side of y. So what if I take another connection? What if I take another connection from here to here? Then if I delete the connection from x to t2, if I delete the connection from x to t2, you can see that this has become a binary tree, and this has become an AVL tree. Okay. So here also, if you perform the in-order traversal, so you have t1 first, then x, then you have t2, then you have y, then you have t3. So this is how you perform the rotation in an AVL tree. Then I will show you a simple algorithm to perform this task. So you have to understand the steps from the algorithm, but you should be able to perform the rotations on paper. So I'm taking this algorithm here. Okay, and if you look at this one, okay, so for rotating the right rotation with respect to with respect to x, these are the assignment that you need to make first. That is, you have to assign x equal to y's left. So here x is y's left, and t2 equal to x right. T2 is obviously x right. Now here we are making the assignments. After rotation, x dot right should be y. So x dot right is obviously y, and y's left should be t2. Y's left is t2. Then we have to update the heights of y and x in order to perform the new balance factor, because obviously the balance factors of every node participated in this particular rotation may change. So we are actually updating the balance factors of, or the heights of x and y, and calculating the balance factor. Similarly, we can perform the rotation to the left also. So suppose that I have a tree. So here I have y, then I have x, then I have t1 here, t2 here, and t3 here. Then here I am performing the right rotation. So with respect to the node, sorry, I am performing the left rotation with respect to the node x. So I am rotating this one in this way. So as I said in the previous case, the x will be the new root. So x is my new root. Now I have t3 on the right side of x, t2 on the left side of x, and similarly on the left side of x I have y, as well as on its left side we have t1. Now if you look at the in-order traversal here I have t1, then y, then t2, then x, then t3. I need to maintain the same order in the tree after the rotation also. So for that, what I need to do is I need to take this link from the left, from x to y. That means if I break this connection and I connect this one to this one, then I will get the new tree. So this will be an AVL tree, because if you take the in-order traversal again, so I have t1, then y, then t2, then x, then t3. So this is how you perform the left rotation. So this is the left rotation. Okay, now if you look at the algorithm to perform this task, we are taking the algorithm here. Okay, so you just look at this one. Here I am returning the value of x. Actually this is done to update the value of the root. That is, after the insertion we will be returning the new value of the root. So in this case new value of the root is x, so we are returning x. That also happens here as well, because we have the new root as x, so we will be returning the value of x, the address of x to be specific. Okay, so this happens like this. If you want to rotate left here, then you are taking x as y's right, x is y's right, and t2 is x left, t2 is x left. Then I'm assigning x left equal to y, x left equal to y, then y's right equal to t2, y's right equal to t2. Then we are updating the heights of x as well as y. Then we are returning the address of x as the new root. Okay, now we will see more about insertion and deletion in the next video. Thank you.